Welcome back to another video by Camroom 5. In today's video of AS level P3, we will be talking about thermometric titrations. Thermo like we mean temperature and metric means measurement. So thermometric means we are going to be measuring temperatures. The principle of this is that when a reaction happens, any reaction, when it happens, there is some enthalpy change associated with that reaction. So there's some enthalpy change involved, whether it's exo or endo. As a result, temperature changes. And when the reaction proceeds, the temperature changes increase. Only until one of the reactant runs out. Or you can say one of the reactant becomes the limiting reactant. For example, in today's video, we'll be dealing with hydrochloric acid neutralizing sodium hydroxide to produce sodium chloride salt and water, which is enthalpy of neutralization. Because the H ions from the acid will be neutralizing the OH ions from the alkali to produce water. That is known as the enthalpy of neutralization. It's an exothermic reaction. Now imagine that I am taking a polystyrene cup and I'm supporting it on a beaker. I have 5 such setups. The beaker is there just to support my polystyrene cup. It's not there to contain the liquids. The polystyrene cup is the container where I will be collecting my acid and my alkali. It's a good insulator, so I am adding alkali over here. Imagine in the first polystyrene cup I am adding 5 centimeter cube of 0.100 mole per decimeter cube sodium hydroxide. In the second cup, I am adding more sodium hydroxide. Imagine, let's say 10 centimeter cube. In the third container, I am having 15 centimeter cube of alkali. In the fourth container, I have the same concentration, but this time it's 20 centimeter cube of the alkali. And let's say in the fifth container, I have 25 centimeter cube of the alkali. Each time I'm going to be measuring the initial temperature, so I'm going to be making a table. Initial temperature / units, final temperature / units, and obviously change in temperature / units, which are degrees Celsius. Hypothetically, my initial temperature was 22.5, 22.1, let's say 22.0, in this range because it's a room temperature. So in the beginning, my initial temperatures were within this range. Now I am adding 15.0 centimeter cube of HCl in each container. This is the same concentration and volume of the same acid. Now obviously we know that in some cases the HCl will react fully, or in some cases the alkali won't be enough to completely neutralize. I measured the temperatures immediately after adding the acid, and you can see on the table the final temperatures. I am not writing the change in temperature on this table because the space wasn't enough, but let's say the final temperatures were these. You can see the final temperatures were increasing but then did not increase as much. To understand it better, let's make a graph with volume of alkali on the x-axis and the change in temperature / degrees Celsius on the y-axis. The change in temperature became more and more when the alkali was added. But with 20 centimeter cube and 25 centimeter cube alkali, it did not increase as much. When we draw a graph, we see there are 2 straight lines which intersect at a certain point. In the beginning, OH minus ions were the limiting factor because the first few containers did not have a lot of alkali. So OH minus ions were the limiting factor. The heat released and the temperature change depended on the OH minus ions. But when a lot of alkali was there, the OH minus ions were in excess. But the H minus ions were limiting factor. So you can see that in some cases OH minus were limiting and some cases H plus was limiting. But when you see the maximum temperature change, the volume, when the alkali was there with the maximum temperature change, you can see on this graph, the maximum temperature change was obtained with the volume that produces maximum delta T. Why does it produce maximum delta T? Because the reaction reached its fullest point. That is because all the H plus ions were neutralized by the alkali. So all H plus ions moles were neutralized, and that is because complete neutralization occurred of those 15 centimeter cube H plus ions that were added. So 15 centimeter cube of 0.100 mole per decimeter cube HCl was completely neutralized to produce the maximum temperature change. This was achieved only through a graph that had two straight lines which intersected each other to give us the volume, which in my case is around 16.5 or like 17ish. So now let's continue this past paper question. It says you are to determine the enthalpy change of neutralization of hydrochloric acid by aqueous sodium hydroxide and also the concentration of aqueous sodium hydroxide. So long story short, we have Fa1, which is sodium hydroxide, and Fa2, which is a 2.00 mole per decimeter cube hydrochloric acid. I'm saying this 2.00 again and again so that you guys get a habit of writing proper concentration. So let me write that the unknown concentration of sodium hydroxide. Fill a burette with Fa1, which is the alkali. Support the plastic cup in a 250 centimeter cube beaker. Use the measuring cylinder to transfer 25 centimeter cube of Fa2, which is the acid, into a 100 centimeter cube beaker. Use the measuring cylinder to add 35 centimeter cube of distilled water to the acid in the beaker. So now it becomes acid plus water. Measure and record in the table below the initial temperature. So Ti has been recorded. Run 5 centimeter cube of Fa1 from the burette into the plastic cup. So long story short, again, you have a plastic cup which is supported by a beaker, and you have another beaker. In one plastic cup you have the alkali with you, and in the other beaker you have the acid plus water with you. They haven't been mixed yet. So add the mixture of acid and water from the 100 centimeter cube beaker to the Fa1 in the plastic cup. Now you are mixing them. Stir carefully and measure the highest temperature obtained. Do it immediately because you don't want to allow the heat to be dissipated to the environment. Rinse the plastic cup. Repeat the experiment using 25 centimeter cube of Fe2, 30 centimeter cube of distilled water, and 10 centimeter cube of Fa1. Notice in the table that every time the volume of Fa2, which is the acid, remains the same. So acid remains the same, but the volume of the alkali is increasing gradually and water decreases gradually. Why is the water decreasing? To make sure the total volume remains the same. In each case, let me make it this way. In each case, you can see the total volume is 65 centimeter cube. So the container at the end of the day, the container which is the plastic cup within the beaker, will have a total 65 centimeter cube solution. Moving on, I have already filled the data for you guys, and you can see the initial temperature was almost 22ish. The final temperature, the highest temperature was 24, 27, 29. It increased and then almost became constant. The temperature change, you can see clearly it's increasing and then it's reaching a constant value. That is because in the initial part, when the alkali was really less, alkali was your limiting reactant. So alkali was the limiting factor, but when excess alkali was added, it means the acid becomes the limiting reactant. So somewhere in the middle, the neutralization would be complete. Let's fill the table On the y-axis will have the temperature change, the x-axis will have the volume of the alkali. So volume of alkali, or you can say FA1 slash centimeter cube, comes here. It's going to be 5, 10, 15, 20, 25, 30, 35, and let's say 40. If you can see, the temperature change is from 2.5ish and the maximum it goes is 9.5ish. So we need to pick a scale which involves all these values. So I can pick it like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is the change in temperature slash degrees Celsius. Now you can see the temperature change was 2.5, 5.5, 8. So temperature changes 2.5, then 5.5, then 8.0. Then we can continue to see it's 8.5, 9.5, 8.0, 8.0. So it's 8.5, 9.5, 8.0, 8.0. 8.0 again is at 35. Now we have to draw the lines. So make sure it says, using these points, draw two straight lines that intersect. So we need to draw two straight lines. Now when we try to draw the lines, my line should start from the origin, because it means that at 0 volume addition there should be no temperature change. My line should look like this, so that 2 points are on the left hand side and 2 points are clearly on the right hand side. Another line should look something like this. Yes. So here I can see the maximum temperature change. Let me draw an arrow for you guys. So maximum temperature change is here, and this represents the volume. So here I can clearly see the volume which drops down. Moving on, the volume of FA1. So this is the point. If I make it a little bigger, this is the point of the volume. If I drop it down, when you'll be doing it on paper, it would be easier for you. The volume I can clearly see is 21, 22. So that is 22.5. No, that's not 22.5. That is going to be 22.3, because it's lesser than 22.5. So my volume is 22.30. The temperature change, I can see the temperature change from here. Let me make it a little bigger. The temperature change is 9.5, 9.6, 9.7, 9.75. So that is 9.75. Temperature change is 9. Instead of writing 9.75, I can put it 10.0, because in thermometer readings we don't have the space for two decimal places, so 10.0. The volume of FA1 at the intersection represents the volume of FA1 which neutralized. The reaction between FA1 and FA2 is shown in the equation below. The reaction is exothermic. Use the information to explain the shape of the graph. So you can see the graph is increasing, and then you can see the temperature becomes almost constant for 2 points. So the temperature increases as reaction between H plus and OH minus ions happen that releases heat. When H plus ions become limiting reactant, the temperature values become constant. Moving on, calculate the amount of the heat release produced in the reaction. Use the temperature change. So you have to find the heat release. Heat release is equals to mass, then specific heat capacity, then change in temperature. So how much mass was there? The container contained a total of 65 centimeter cube solution, which means 65 grams. So 65 grams, because for water, by the way, for water or solutions which are aqueous, 1 centimeter cube is equals to 1 gram, because density is equals to 1 gram per centimeter cube. The change in temperature is going to be, we just found that out, that it was 10.0 and the specific heat capacity is 4.3. So we can multiply that and we can get the answer for heat. I'm not solving it here, you can do that. Calculate how many moles of hydrochloric acid. Moles is equals to concentration and volume divided by 1000 to convert it into decimeter cube. If we go back, we can see the concentration of the acid was 2 and the volume of the acid each time was 25-ish. So 25 times 2 and divided by 1000. So it's going to be 0.050 mole per decimeter, moles. Use your answer to E and F to calculate the enthalpy change. So enthalpy change is just going to be heat you found divided by number of moles. Sign is going to be negative and estimated value should be around 57-ish. Make sure you have to find kilojoules, so make sure that it is divided by 1000 also, because you have to find in kJ. Explain why the total volume of solution used was kept constant. You keep the volume constant so that whenever the change in temperature was recorded, you can see the change in temperature dependent on the heat. With different masses of water, with different volumes of water, the heat obtained into the water, the overall change in temperature would also be affected. So you can say, to make sure that the temperature change depended on the heat released only, to keep mass of solution constant. Otherwise, if the mass of the solution changed, the heat released wouldn't be the only factor controlling delta T. That is why we want to make only one factor changing, other factors remain the same. Calculate the concentration in mole per decimeter cube of aqueous sodium hydroxide. So that is again easy. You can see the volume taken is 22.3, right? So you can see moles of H plus ions is equals to 0.050 mole. This is the acid that you used. Moles of H plus and moles of OH minus ions have a ratio of 1:1. So moles of OH minus ion is equals to 0.050 mole. Concentration is equals to moles divided by volume in decimeter cube. So concentration is equals to 0.050 divided by 22.3 divided by 1000. You'll fit your answer here. A student thought that the experiment was not accurate because the temperature changes measured were small. Suggest a modification to the experimental method used in order to give larger changes in temperature. So for larger changes in temperature, you need more H plus ion mole with more OH minus ions should be used. And how can we do it? We can do it by use more concentrated acid and alkali. So temperature change would be more, and when temperature change is more, the percentage error would decrease. Experiment 1 to 7 were repeated using 1 mole per dm cube sulfuric acid instead of the 2 mole per dm cube hydrochloric acid. On the axis below, indicate an appropriate temperature scale and sketch the graph for the temperature changes. So it's going to be very similar, right? It's going to be very similar like this. Why? Because 1 mole sulfuric acid and 2 mole hydrochloric acid. Both release double H plus ions. HCl because of the 2 mole concentration and sulfuric acid because of the diprotic nature. So 1:1 ratio, so graph is going to remain the same. I hope this question is clear for you guys. Stay tuned guys. Thanks.